Welcome to part 5 of the immune system, and this is on our handout. So we're going to be doing this entire workup on the handout now. And we have this little constellation. It doesn't necessarily need to be exactly this constellation because it could happen in parts. Okay, but I've decided to put it together into a single constellation so I can talk about everybody in the constellation. Okay, so you know what the necessary parts are. So when you take a look at your handout, you'll see a monocyte or macrophage. The macrophage is the monocyte that has left the bloodstream. And basically, this is a chronic issue here. It takes some time for seroconversion to happen, which is what this is all about. This is the initiation of the immune response. Okay, notice that we have two basic pathways here. We have the cell-mediated immunity, which is this portion above the dotted line. Then we have humoral immunity, which is this portion below the dotted line. So we're going to be spending some time with these parts and pieces of the program. Okay, and we're going to have a monocyte or a macrophage here in the chronic status. This is an antigen-presenting cell. It's going to present on its surface an antigen. Look at that. There's the antigen right there. Here's the antigen. Here's the antigen. In junior high school, I sat across from this person who used to like to eat food and open his mouth widely to show everyone at the table the fabulously and wonderfully disgusting appearance of the food in his mouth. He was presenting what he had eaten. It just always reminds me of that certain sense of pride that goes with the macrophage here presenting the foreign antigen. So imagine that this cell has eaten an HIV virus or any other pathogen in the body, and it's presenting it now. And we have T helper cells, also known as T cells, T4, as it were, CD4 cells. And we have B cells. These are lymphocytes, okay? And they have the capability of rearranging their own DNA. This sort of breaks the rules of Watson's central dogma of, what does DNA, RNA, and protein do in the central dogma, because he had not accounted for the rearrangement of proteins, or rather DNA and genomes. So their genomes can be rearranged 3 times 10 to the 8th different ways in order to produce a receptor that identifies a foreign antigen. 3 times 10 to the 8th different antigens can be identified. The T cell, all of these cells are meeting up with each other, and they're meeting whenever you see a class 1 or class 2 molecule. That's a name tag that says, "Hi, it's me." Okay, hi, it's me. Hey, it's me. And so when you have the MHC name tag bonded to plus the foreign antigen, suddenly there's an activation. Okay, that means, you have to have 2 keys to turn the lock of this particular lock. And then the macrophage will send out interleukin 1. Interleukin 1 activates the T helper cell. That's all it does. Finished. Story over. Interleukin 2 comes from the T helper, the T4 cell, and self-activates, and then also activates the T cytotoxic up here in the cell-mediated immunity situation. Okay. Then the T helper has other interleukins, which I don't even keep track of anymore, because I still like the original names back from the 1990s called B-cell growth factor and B-cell differentiation factor, because they're more vividly named. And they cause the B-cell to grow up and differentiate and become either a plasma cell or it becomes a memory cell. Okay, first usually a plasma cell, which goes through the release of immunoglobulins or antibodies. And it goes through the release of immunoglobulins in this order. It creates the mu molecules, the delta, which is a surface molecule. It collects the mu molecules and sends them out with the gamma molecules eventually. And so we have the antibody called IgM and IgG. Okay, these are the only two that can activate complement. Okay, and then the IgG has another factor that it crosses the placenta. So when the mother is pregnant with a baby, an embryo or a fetus, that particular developing individual is being protected by mom's immune system through immunoglobulin G. After birth, mom has immunoglobulin A, that's a digestive immunoglobulin present in both tears, respiratory system, and in the digestive system, and it's released in mother's milk. And so that's the second way in which the developing individual, the neonate, is protected by having mother's milk. Okay, and it's a dimer. It's a very unique little molecule. We don't get to immunoglobulin E until we get to a place of genuine, how shall I say, chronic development, usually allergic reactions, and it could lead to anaphylaxis. But ultimately, it seats itself in the mast cell, and we just have inflammatory experiences. Okay, so that's that particular page right there. We're going to be able to identify a lot of things. Or I'm going to go over the, how would I say, why don't I do that right now? There's a number of things that can be interfering. If you have a viral infection, normally we deal with one viral infection at a time, partly perhaps because of the release of interferon. It's turned out that we've discovered that HIV can be prevented if the individual is actually experiencing a mild type of viral infection prior to the exposure of HIV. And these individuals tend not to be subject to infection by HIV. So kind of a lucky break for them. We have interferon. We also have phagocytosis. We have antibodies that can be specific for virally infected cells. We have cytotoxicity, which is the cell-mediated immunity. Let's come up here and note that something akin to IgD or IgG gets established on the surface of a T cytotoxic cell, and it comes over this way. And now we have sort of like a little unicorn. Okay, this guy right here, the T cytotoxic cell, can destroy a tumor cell that it identifies, or a virally infected cell that it identifies as being infected by a virus. How does it do that? Is that it actually sends out something like Mac Attack, little hollow spears, and we have lysis of the cell. How do we know that we have a tumor cell? Tumor cells are cells that revert to the prenatal state and produce prenatal proteins, growth factors, from embryological and fetal development. So basically that's what oncogenesis is. Oncogenesis is intended, shall we say. It's meant to happen. It's meant to happen from the time of conception to the time of birth, because oncogenes are growth genes that cause the fetus and or the embryo and the fetus to develop to the stages of birth. And then they're supposed to all go off. And we're not supposed to have those genes go on anymore. So that's the intention here. Okay. You'll come down here and you'll notice that we get an initial infection. The virus is alive and well. We get interferon. We get this little area of here of illness that's described. The person is experiencing signs and symptoms. Notice that we seroconvert, we produce the antibody, and the illness comes to an end, the interferon tapers off, and now we have, how shall I say, memory. Okay? And the memory gets a booster if we get exposure again. Oftentimes when we get a vaccine, a single vaccine is not adequate to give us sufficient levels of immunity. And so we actually need a booster vaccine to get our immune levels up there. This is going to be immunoglobulin G. Okay, that's the memory globulin right there. Over here, we have this little, again, going through it, we have this incubation period. There's an interferon development here. Here we have cell-mediated immunity, okay, that we're looking at. We have immunoglobulin M, which activates, or NG as well, which activates cell-mediated immunity. Okay, that's the acute phase of illness. We get convalescence, and then we get immunity at the end.